Paris, 1884. The French government announced something unprecedented, a World's Fair to celebrate the 100th anniversary of the French Revolution. They wanted a monument, something bold, something that had never been done before. Enter Gustave Eiffel, a 52-year-old engineer who had already made his name building iron railway bridges across France. But this project would be different. This would be a tower reaching 1,000 feet into the sky, taller than any structure humanity had ever built. The idea wasn't entirely new. Eiffel's engineers, Maurice Koechlin and Émile Nouguier, had sketched the initial concept 2 years earlier, a massive iron lattice tower, standing on 4 curved legs that would meet at the top. When Eiffel saw their drawings, he recognized something revolutionary. This wasn't just architecture. This was a statement about what engineering could achieve. But Paris wasn't ready to embrace it. Artists, writers, and intellectuals launched a campaign against the tower before a single beam was raised. They called it a metal monstrosity, an eyesore, a disgrace to the beauty of Paris. One famous petition described it as a gigantic black smokestack that would overshadow Notre Dame and the Louvre. The criticism was fierce and relentless. Eiffel responded not with emotion, but with mathematics. He defended his design with calculations, stress tests, and wind-resistant studies. The tower, he argued, would demonstrate French engineering prowess to the entire world. And on January 28, 1887, despite all opposition, construction officially began. The challenge was immense. No one had ever built anything close to 1,000 feet tall. There were no computers to model structural stress, no software to simulate wind loads, no digital tools to check if the mathematics were correct. Everything depended on human calculation, slide rules, and hand-drawn blueprints. Gustave Eiffel and his team had only their minds and their experience. Maurice Koechlin led the mathematical work. Every angle, every joint, every beam had to be calculated by hand. The tower would need to withstand tremendous forces, not just its own weight, but wind pressure that could topple it if the design was flawed. Koechlin developed equations to distribute stress evenly across the structure. He calculated that the tower's curved legs would transfer all weight safely into the foundation. The design was elegant in its efficiency. The lattice framework meant the tower would be mostly empty space. Wind would flow through it rather than pushing against a solid surface. This was counterintuitive. Most engineers of the era believed tall structures needed to be heavy and solid. Eiffel proved them wrong with mathematics. Architect Steven Sauvestre refined the aesthetic elements. He added decorative arches at the base, pavilions at each level, and a rounded top. These weren't just for beauty. They served to make the tower more acceptable to skeptical Parisians. Every detail was sketched by hand, then translated into precise measurements. By the time construction began, the team had produced over 5,300 workshop drawings. Each of the 18,038 iron components was designed individually. There was no room for error. The tower would consume over 7,300 tons of iron. But not just any iron. This had to be wrought iron of exceptional quality, capable of bearing enormous loads, while remaining flexible enough to expand and contract with temperature changes. The metal was sourced from forges across France, then transported to Eiffel's workshop in Levallois-Perret, just outside Paris. Here, the real precision work began. Each of the 18,038 metal parts had to be fabricated to exact specifications. Workers heated iron bars and furnaces, then shaped them using massive hydraulic presses and steam hammers. Riveters prepared millions of holes that would later join the components together. The tolerance for error was minimal, often just 1/10 of a millimeter. What made this truly remarkable was the prefabrication method. In 1887, building on site was standard practice. Eiffel revolutionized the process. Every single component was manufactured in the workshop, tested for fit, then disassembled and transported to the construction site. When pieces arrived at Champ de Mars, they fit together perfectly, like a massive metal puzzle designed with absolute precision. The rivets alone numbered over 2.5 million. Each one had to be heated until red hot, inserted through pre-drilled holes, then hammered into place before it cooled. This created joints stronger than welding. Teams of 4 workers, a heater, a holder, a striker, and a backer, worked in perfect coordination. The sound of hammering echoed across Paris as the iron giant slowly took shape. Now, quality control was ruthless. Eiffel personally inspected components. Any piece that didn't meet specifications was rejected and remade. This uncompromising standard ensured structural integrity that would last generations. January 1887. The foundation work began in the freezing Parisian winter. Workers excavated massive pits for each of the tower's 4 legs. The challenge was immediate. The construction site sat on unstable soil near the Seine River. On the riverside, the ground was waterlogged and weak. Eiffel's solution was ingenious. He designed massive concrete foundations, some reaching 16 feet below ground level, using compressed air caissons, watertight chambers that kept water out while workers dug deeper. Each foundation block was enormous, designed to distribute the tower's immense weight across a wider area. The precision required was extraordinary. All 4 foundations had to be perfectly level with each other, despite being separated by over 400 feet. The engineers used water-filled tubes as primitive levels, checking and rechecking measurements constantly. A single miscalculation would mean the entire tower would be crooked. By July 1887, the foundations were complete. Now came the real test, assembling the iron framework. The first stage involved raising the tower's 4 massive legs from ground level to the first platform, 187 feet up. This was the most dangerous phase. The legs stood at sharp angles, creating complex geometric challenges. Traditional scaffolding wouldn't work. Eiffel designed custom wooden scaffolds that could be adjusted as the iron legs rose. These temporary supports had to bear tremendous weight while allowing workers to install the iron pieces. Teams worked on all 4 legs simultaneously, racing against time and weather. So each iron component had to be lifted into position using steam-powered cranes, cutting-edge technology for the era. The assembly was astoundingly accurate. When the 4 legs finally met at the first platform, they aligned within millimeters of the planned position. This was precision engineering on a scale never before attempted. With the first platform complete in March 1888, the tower stood 187 feet tall, already higher than most buildings in Paris. But this was only the beginning. The second stage would prove even more challenging. From the first platform to the second, 380 feet up, the tower's legs began to curve inward more dramatically. The angle changed constantly as the structure rose, requiring continuous mathematical recalculation. The wooden scaffolding used for the first stage couldn't reach these heights. Eiffel's solution was brilliant. He used the tower itself as its own support system. Workers installed temporary platforms that moved upward as construction progressed. No, these weren't fixed scaffolds, but adjustable frameworks attached directly to the iron structure. It was construction innovation born from necessity. Weather became a formidable enemy. High winds at these elevations made work impossible on many days. Workers had to time their efforts carefully, working only when conditions allowed. Rain turned metal surfaces dangerously slippery. Winter cold made iron brittle and difficult to work with. Yet despite these obstacles, the riveting teams never stopped their rhythm. The hammer blows continued day after day, joining iron to iron. Safety was a constant concern. Workers operated hundreds of feet above ground with minimal protection. Yet remarkably, Eiffel implemented safety measures advanced for his time. Nets were installed below work areas. Now, workers used safety belts, uncommon in 1880s construction. The site had a medical station. These precautions saved lives. During the entire construction, only one worker died, an extraordinary safety record for such a dangerous project. By June 1888, the second platform was complete at 380 feet. The tower now dominated the Paris skyline. What had seemed impossible was becoming undeniably real. The third and final stage presented the greatest engineering challenge yet. From the second platform to the top, the tower would rise another 600 feet, a massive distance supported by an increasingly narrow structure. The four legs now merged into a single tower shaft, concentrating all weight onto a smaller framework. The mathematics became even more critical. Any miscalculation at this height could prove catastrophic. The summit would house equipment and observation areas, adding significant weight at the highest point. This went against traditional engineering wisdom, which suggested keeping heavy loads as low as possible. But Eiffel's calculations showed the lattice design could handle it. The open framework would allow wind to pass through rather than creating resistance that could destabilize the structure. Construction at these extreme heights tested human endurance. Workers climbed hundreds of feet daily, carrying tools and materials. The wind was relentless. Strong gusts could knock a person off balance. The psychological challenge was immense. Looking down from 700, 800, 900 feet required nerves of steel. Yet these workers persevered, driven by pride in their unprecedented achievement. The iron framework for the top section was lighter and more delicate than below, requiring even greater precision. Riveting teams worked in cramped conditions on narrow platforms. Every component had to be lifted by crane from the ground, a process that became more difficult and time-consuming with each additional foot of height. Progress slowed, but it never stopped. On March 31, 1889, Gustave Eiffel himself climbed to the summit and raised the French flag. The tower stood complete at 1,063 feet, the tallest structure in the world. 2 years and 2 months of relentless work had transformed a controversial vision into magnificent reality. The Eiffel Tower opened to the public on May 15, 1889, as the entrance arch to the World's Fair. Over 2 million people visited during the exposition, climbing the tower's stairs or riding its hydraulic elevators, another engineering marvel in themselves. The same critics who had denounced the project now stood in silent admiration. What had been called an eyesore became the symbol of Paris itself. The numbers behind the achievement were staggering. 18,038 individual iron pieces, each precisely manufactured. 2.5 million rivets, each heated and hammered by hand. 7,300 tons of iron, shaped and assembled without computers or modern machinery. 300 workers laboring for 26 months. And most remarkably, only one fatality during construction, an unprecedented safety record for such an ambitious project. But the true triumph was in the engineering principles Eiffel proved. He demonstrated that height didn't require mass. The tower weighs only 10,100 tons, remarkably light for its size. If you melted it down and spread the metal across its base, it would form a layer only 6 centimeters thick. The structure's strength comes not from bulk, but from intelligent design and precise mathematics. The tower validated the power of prefabrication. Every component manufactured in the workshop, tested for fit, then assembled on site with minimal adjustment. This method revolutionized construction practices worldwide. It proved that complex structures could be built faster, safer, and more accurately through careful planning and precise manufacturing. Wind resistance calculations were equally groundbreaking. The lattice framework that skeptics had mocked became the standard for tall structures. Modern skyscrapers still use variations of Eiffel's principle, allowing wind to pass through rather than pushing against solid surfaces. His mathematical approach to wind loads influenced structural engineering for generations. The Eiffel Tower was initially meant to be temporary. The permit granted to Gustave Eiffel allowed the tower to stand for only 20 years after the 1889 World's Fair. It was scheduled for demolition in 1909. But by then, the tower had proven far more valuable than anyone imagined, not as art or architecture, but as a scientific instrument. The tower became an invaluable platform for meteorological observations, studying weather patterns at different elevations. Scientists used it for physics experiments, dropping objects from various heights to study gravity and air resistance. Most importantly, it became crucial for radio transmission. The tower's height made it perfect for mounting wireless telegraph antennas. During World War I, and it intercepted enemy communications, proving its strategic military value. This utility saved the tower from destruction. What began as a temporary exhibition piece became a permanent fixture because it served practical purposes. Beauty alone hadn't guaranteed its survival. Usefulness did. The tower transformed from controversial art into essential infrastructure. Today, over 135 years after construction began, the Eiffel Tower still stands as the ultimate testament to pre-digital engineering. Built with hand calculations, slide rules, and human determination, it has withstood over a century of weather, wind, and time. Modern analysis confirms what Eiffel calculated by hand. The structure is sound. The mathematics were perfect. The tower receives over 7 million visitors annually, making it the most visited paid monument in the world. It has become more than a structure. It's a symbol of human capability, proving that revolutionary achievements don't require advanced technology. They require vision, precision, courage, and the willingness to prove skeptics wrong through sheer excellence of execution. The Eiffel Tower stands as proof that true innovation transcends the tools available. It's a reminder that human ingenuity, mathematical rigor, and unwavering determination can accomplish what seems impossible. Built without computers, without modern machinery, without digital modeling, yet perfect in its execution. An iron giant that changed how humanity builds and continues to inspire engineers 135 years later.